This lecture is part of a series of lectures on rings and modules and will be about factorization of polynomials. More precisely, it would be factorization of polynomials with integer coefficients. So last lecture we saw that the ring of polynomials with integer coefficients had unique factorization, so every polynomial can be written as a product of irreducibles in an essentially unique way. And the first thing we want to ask, is there an algorithm for doing this? So, and what we want is an algorithm that, given f, will write f as a product of irreducible polynomials or primes. And the first algorithm for doing this was found by Kronecker and works as follows. It uses the fact that if two polynomials g1 and g2 are equal at more than n points, where n is equal to the degree of g1 or g2, then g1 equals g2. And that's sort of obvious because the polynomial g1 minus g2 must vanish at more than n points, so it must be identically 0. And now what we do is, suppose the degree of f is equal to n. Then any factor of f must obviously also have degree at most n. So what we do is we pick any n plus 1 points, a1 up to a n plus 1, and we look at f of a1 up to f of a n plus 1. And now if f is equal to g times h, then ga1 divides f of a1 and so on up to g a n plus 1 must divide f of a n plus 1. And you see from this that there are only a finite number of possibilities. Unless f of a1 is equal to 0. Well, if f of a1 equals 0, then we found a linear factor of f, so we may as well assume that all these numbers are non-zero. So there are only a finite number of possibilities for ga1 up to gan, and since these numbers determine g by what we just said, this indicates there are a finite number of possibilities for g, and we can just test each of these to see if they divide f. Notice, by the way, that this algorithm is pretty slow. It's slow for two reasons. First of all, we have to factor these integers f of a1, f of a2 and so on, and factorising large integers can be still a little bit difficult. Secondly, there are an exponentially large number of choices to check here. So, for example, g of a1 might be 1 or minus 1 or some other factor of f of a1, but there are at least two choices. So there are going to be more than 2 to the n choices for all these g's, so we have to check at least 2 to the n possible polynomials, and this is exponentially large in n and maybe rather slow. We notice that Kronecker's algorithm can also be extended to polynomials in several variables. I'm not going to give details, but you can vary it slightly so that it still works with several variables. So we can factor polynomials in several variables into irreducible factors in an algorithmic way. A very similar problem asks, does a polynomial f in z x1 xn have a 0 in z to the n? Finding a 0 doesn't sound too difficult from factorising a polynomial. In fact, it seems, for polynomials in one variable, it's just a special case of factorising it. But rather surprisingly, that there is no algorithm for solving this in general. This is actually Hilbert's 10th problem. So Hilbert had this famous list of about 23 unsolved problems, and the 10th problem was to find an algorithm to tell whether a polynomial has integer coefficients. And I think Hilbert was expecting a positive solution to this. However, it turns out there's no such algorithm. This was shown by Julia Robinson, Matija Savich, Davis and Putnam. So Matija Savich did the last step of the proof, so it's sometimes named his theorem. So they showed that there's just no algorithm in general that will always decide whether or not a polynomial has a root. Obviously, if a polynomial does have a root, you can find it just by testing all possible roots one by one. It's very slow, but it's an algorithm. The problem is that if f doesn't have a root, it may be very difficult to decide whether or not it has a root. I mean, you can't check an infinite number of roots because this takes an infinite amount of time, and in general there's just no way of doing it. Roughly speaking, what they did is Turing showed you can't solve the halting problem for Turing machines. There's no algorithm that will tell you whether a Turing machine halts. And roughly speaking, they showed how you can encode any Turing machine into a polynomial with integer coefficients such that the Turing machine halts if and only if the polynomial has a root. And so since the halting problem for Turing machines is unsolvable, the problem of whether a polynomial has a root is unsolvable. As we said, Kroneker's algorithm is really slow. We can ask, is there a fast algorithm? And the answer is sort of. If we've got a polynomial, we can write f as its content times a polynomial with co-prime integer coefficients. And there's a fast algorithm for factorising this bit of it, the polynomial with co-prime integer coefficients. This is the LLL algorithm, named after Lenstra and Lovász. I'm not going to give details because it's a little bit too complicated for an introductory algebra lecture. But it's polynomial time, so it gives a fast answer to factorising this. The other bit is actually rather harder. So this is just an integer. And at the moment, it's unknown if there's a fast algorithm for factorising integers. So fast means, say, polynomial time in the number of digits of the integer. We've got some reasonably fast algorithms that will work for integers with up to about 100 digits, or probably more by now, but they're not polynomial time, and we really get stuck for integers with, if an integer had, say, 1,000 digits, we probably couldn't factorise it. Actually, in some sense, we do have a polynomial time algorithm for factoring integers, which was found by Shaw. There's a slight catch. This algorithm is for quantum computers. At the moment, it's not quite clear how fast or large quantum computers are. The problem is there's a lot of hype and exaggeration by the people making quantum computers in an effort to get more funding. As far as I can figure out, the best quantum computers at the moment have around 50 to 100 quantum bits, whereas to do some serious integer factoring, you'd probably need somewhere of the order of 1 million quantum bits in your computer. So we're probably still a decade or two away from being able to factorise integers in polynomial time, even with a quantum computer. Notice the rather odd thing that if you're trying to factorise a polynomial, the hard case is degree 0 polynomials that are integers. For degree greater than 0, we do in fact have a fast algorithm for doing it. So now I will talk about the problem of testing f for irreducibility. So here we're not asking to factor f, we're just asking whether or not f is irreducible. This is usually an easier question than factoring f. For example, if we've got an integer, It's usually reasonably easy to tell whether it's prime or not, even if it's very big, by using we even have polynomial time algorithms for it, but there are also various probabilistic tests, whereas it's still hard to factorize. And the same is true for polynomials. It's easier to test them for irreducibility than to factorize them. So the first thing we note is that almost all polynomials of degree greater than 0 and with content 1 are irreducible. This is over the integers. And this is actually maybe a bit surprising because over the integers, most numbers are not prime. I mean, if you look at a random 100-digit integer, the chance of it being prime is well under 1 in 100. So most integers are composite. However, for polynomials over the integers, most of them are irreducible. For instance, degree 1 polynomials with content 1 are always irreducible. If you've got a degree 2 polynomial, it's probably going to be irreducible unless the discriminant is a square or something like that. And being a square is kind of unusual for integers. So if you have to guess whether a random polynomial is irreducible, you guess that it's irreducible. Well, if guessing isn't good enough, the next easiest thing to do is to look at it modulo a prime p. For example, is x to the 4 minus 3x squared plus x minus 5 irreducible? Well, it's probably not immediately obvious, but if you look at it modulo 2, it's x to the 4 plus x plus 1, which is irreducible mod 2. And any factorization of this over the integers can be reduced to a factorization mod 2, so this is indeed irreducible because it's irreducible mod 2. By the way, when you use this, you have to be a little bit careful that the leading coefficient is 1, because if we take a polynomial like 2x squared plus x, this is irreducible mod 2, because mod 2 it's just x, but it's not irreducible. It's obviously divisible by x. The problem here is the leading coefficient is divisible by 2, which means when you reduce it mod 2, the degrees of polynomials drops, and if the degree of a polynomial drops, then weird things can happen, like an irreducible polynomial might become a unit if its degree drops. So when you test polynomials mod p, just watch out for make sure the degree doesn't drop. Next we have the Eisenstein's criterion. So this is one of these things that's like DeLopitals Rule that absolutely everybody remembers. So I'll just review this very quickly. So Eisenstein says that if x to the n plus a n minus 1 x to the n minus 1 plus a naught has the following properties. So this is going to be a polynomial with integer coefficients as usual. So if it satisfies, first of all, a naught, a1 up to a n minus 1 are divisible by p, which is some prime over the integers. And secondly, p squared does not divide a0, then f is irreducible. And the proof of this is very easy. So if f is equal to g times h, where g is equal to x to the m plus all the way up to b0, and h is equal to x to the n minus m plus all the way up to c0, then from the fact that a0 is divisible by p but not p squared, we must have one but not both must be divisible by p. And we may as well assume that b0 is divisible by p. So let's assume that b0 is divisible by p. And then you look at all the coefficients of this that are divisible by p. For instance, we might get up to bk, which is divisible by p. And there might be some bk plus 1, which is not divisible by p. And there must be some not divisible by p because the leading coefficient is not divisible by p. And then if you look at the coefficient of x to the k plus 1 in GH, you notice that it's sum of b0 up to bk times something, which is divisible by p, plus bk plus 1 times c0, which is not divisible by p. So the coefficient of x to the k plus 1 is not divisible by p, and this contradicts the fact that all the coefficients of f, apart from its leading coefficient, are divisible by p. Well, there's a standard example of this. The main use of this is to show that the polynomial whose roots are primitive pth roots of unity, which is this one here, is irreducible. And at first sight, Eisenstein's criterion doesn't seem to be very promising for this polynomial because absolutely none of its coefficients are divisible by p. But there's a cunning trick you can do. We can change x to x plus 1 and we get x plus 1 to the p minus 1 over x, which is now x to the p minus 1 plus p, x to the p minus 2 plus p choose 2, x to the p minus 3 and so on plus p. And now we notice that all these coefficients are divisible by p because they're just binomial coefficients. And we also notice that this is not divisible by p squared. So by Eisenstein's criterion, this polynomial and therefore that one are irreducible. This looks like a sort of very weird ad hoc trick that just randomly works for this particular polynomial if we make this strange change of variable. There is actually a good explanation for why this works. The point is that p has a property called totally ramified in the ring of integers generated by a primitive pth root of unity. So zeta to the p is equal to 1 and zeta is not equal to 1. So this is called a cyclotomic field. And what do we mean by saying p is totally ramified? Well, what that means is that p is equal to a unit times a power of a prime in this ring of integers. And it turns out to be a unit times a power of 1 minus zeta. And the fact that you're taking 1 minus zeta accounts for why you have to change x to x plus 1 here, because 1 minus zeta is going to be a root of this polynomial here. And it turns out that whenever you have a prime that's totally ramified in some extension field, in other words, it's the power of some other prime, then you get an analogue of Eisenstein's criterion, and you can use it to prove that the polynomial defining this field is irreducible. So Eisenstein's criterion is really a criterion for totally ramified fields. For more about that, you need to go to learn about algebraic number theory. So for the next example, let's start with a historical example. So back in the 19th century, people were very interested in factorising expressions like p to the n plus or minus 1. And you can, for instance, do 2 to the 58, and this is an obvious factor, which is 5. And it's got two other factors, 107367629 times 536903681. And this was found after immense labour by some guy Landry in 1869. And you must remember that this was way before computers. I mean, this wouldn't be hard to do on a computer, but Landry did this entire factorisation by hand, and how he found this I have simply very little idea. I mean, you can restrict the factors of this to some extent. For instance, they must be 1 mod 4 because this is a sum of two squares, and this is divisible by 29, which probably says the factors must be 1 mod 29 or something like that. He apparently spent years doing this calculation. Well, he must have been a bit disappointed when in 1871 oriforillion pointed out that you can find this factorization in about 10 seconds by using the fact that 4a to the 4 plus b to the 4 unexpectedly factorizes as 2a squared plus 2ab plus b squared times 2a squared minus 2ab plus b squared. And we notice that if we put a equals 2 to the 28 and b equals 1, then we've got a factorization of this number here, which essentially gives this factorization with almost no effort. So factorizations like these are called oriforillion, I don't quite know how to pronounce it, factorizations. The point is you sometimes get polynomials that look as if they're irreducible at first sight, but turn out to be reducible. So a simple example of this is x to the 4 plus 4, which turns out to be x squared plus 2x plus 2 times x squared minus 2x plus 2. And in general, whenever you get a polynomial that's the sum of a very small number of monomials, you should be a little bit suspicious that maybe it's got an unexpected factorization. There's another, as an example of this, just have an exercise. This was a problem going around the internet a few years ago, which is that n to the 4 plus 4 to the n is never prime for n greater than 1. And if you work out n to the 4 plus 4 to the n for a few small values of n, it's quite often not at all obvious that it's not prime. I mean, sometimes its smallest factors are quite big, but it shouldn't be too difficult to do it using these funny factorizations. By the way, 4a to the 4 plus b to the 4 is not the only sort of monomial that has this weird factorization. If you look this up on Wikipedia, they give several other examples of these sorts of funny factorizations. So finally, we will just talk about linear factors. So linear factors are easy to find because if we've got a polynomial x to the n plus a n minus 1, x to the n minus 1 plus a 0, all linear factors x minus alpha, with alpha in z, satisfy alpha divides a 0. And this follows easily. For example, it's a special case of Gauss's lemma. This means that linear factors are easy to find. We just have to run through the divisors of a0. And if the degree n is less than or equal to 3 and the polynomial is reducible, it has a linear factor. So this means that for polynomials of degree 3, it's quite easy to check for irreducibility. We just have to check the factors of a0 to see if they're linear factors. For example, suppose we've got a polynomial x cubed minus 3x plus 1. This is irreducible because the degree is less than or equal to 3 and it has no linear factors. And to do that, we just have to check the factors plus or minus 1 of the constant term 1 and not roots, which is kind of obvious. You could also do this polynomial by noting that it's irreducible mod 2. I mean, there are lots of ways of doing it. This particular polynomial turns up because its roots are, you can check that its roots are 2 cosine 2 pi over 9, 2 cosine 4 pi over 9, and 2 cosine 8 pi over 9. And these numbers turn up if you try to trisect a 60-degree angle by ruler and compass. If you want to trisect a 60-degree angle by ruler and compass, it's more or less equivalent to constructing these numbers. And it's not too difficult to check that if you can construct a number by ruler and compass, then its irreducible polynomial must have degree a power of 2. And here we found an irreducible polynomial with these as roots whose degree is obviously not a power of 2. So the fact that this polynomial is irreducible shows that you can't trisect angles by ruler and compass. In fact, you can't even trisect a 60-degree angle with ruler and compass. Okay, I guess that's all about polynomials for the moment. Next lecture will be on Noetherian rings and modules.